All right, greetings, Saintsmen. We're gonna get going here. My apologies for getting moving a little late. Um, no excuses. Just I was just being a boomer. What I know how to do with some of the features on this. So here we go. So for lesson 1.4, we're going to discuss the permanent area within a coordinate plane. So the first thing that we need to actually discuss is what a polygon is. So let's get going here. And I hope to make this lecture a little bit shorter than the one that previously existed for you guys. In I've promised that now twice so far, and I've actually been longer each time, except for the practice quiz that I had in comparison to a video that no longer exists for you guys. But a polygon. Ooh, look at that, guys! My thing wants to reboot right now. How tragic would that be? We're gonna go ahead and snooze that guy. A polygon. I'm on the timer now. 30 minutes. Polygon is a geometric figure um, that is composed of a minimum of, and we're going to have a little bit of suspense here. So a polygon on how many sides it may have, and how many line segments compose those sides. And we have to think about what actually makes sense here, what actually is possible. So one line segment does not make a polygon, right? So just oops, uh, let's take a look. I can just draw one of these guys, right? Or technically, two line segments won't make that. That's just an angle. So what we need to have is a minimum of 3 line segments. And within that, we have each side is going to intersect exactly 2 sides. And at each, there is a vertex. So this is what we are going to take a look at. I'm going to give you guys a few different examples, and my software isn't really awesome right now at correcting my straight lines because you guys, we've just discussed this before. Saintsman, my drawing is pretty bad, and I need the rescue of software to kind of straighten things out for me. But these ones I intend to be as perfect as they are in my mind. They are not perfect in the screen, but these are intended to be line segments. And here, I'm going to uh, really solidify the points with these little dots here. And we're going to question whether or not is this a line segment? Okay? Like, is a line segment? And the answer is, are these all line segments? And the answer is yes. And is this a polygon? So we have a minimum of 3 sides. All of them are line segments. And they intersected exactly 2 sides. So the answer is going to be a yes. Versus this guy. I want you guys to take a look. And so, spoiler alert. I have a segment. Oops. Oh, goodness gracious. Let's see if I can back that guy up. There's got to be like a backup feature here. Undo. There we go. Here we go. So I have 2 line segments, correct? So this is not a polygon right now. Now let's give it a 3rd line segment. Here's one right here. Boom. But does it in each vertex intersected exactly 2 sides? So this guy is yes, right? Intersects at 2 sides. This guy, sure, but this vertex right here, the issue is that I have this guy hanging out right here. Doesn't intersect at 2 sides, so this is going to be a no, right? Not going to be a polygon. Now, some of you guys have learned this whole thing, open figure, closed figure, right? So like if I had this thing right here, right, 1, 2, 3, 4 line segments, that's not a polygon, but it doesn't all exact, right? That was the issue, 2, 3, 4. This vertex right here only intersects one side right here. So that's really the issue with it, not that it's open or closed. Okay. How about this guy? I'm gonna give you guys a real fun one right here. Okay, line segment, line segment. So I have 1, 2, 3, 4 vertices. Question: is this a polygon? And guess what? The answer is yes. This is actually what the issue is, because some of you guys are looking at this thing like, man, that thing is really ugly looking. Don't be a judge. That's pretty rude. The issue you guys have is with this vertex, I think right here. His issue is that he's actually concave versus being convex. And we're going to talk about what that even means in just a moment. All right. But yeah, it meets the definition. It's got four sides, minimum of three. So it's got, more than three. It's got four. And then, every single vertex connects with two other vertices. So we're good to go. Now, and let me go ahead and use a different color here. Got 1, 2, 3, 4. This is a concave quadrilateral. This is actually a chevron, is the name of it. But yeah, he's actually indeed a polygon. Now, here's where we're gonna come up with an issue of where like, okay, if that guy works, how about this one right here? Now we have 1, 2, 3. Got three sides, it seems like, but the answer here is going to be a no in terms of are you a polygon. You know why? It's this thing right here. It's not a line segment, right? Line segments are not curved. Take you guys through defining some of our polygons. You guys need to memorize the following table, okay? There's the number of sides, and I'm going to go through this rather quickly. The name of the polygon. You guys can go ahead and stop this as you need to. But we're going to go through with all these number of sides of 3, 4, 4, 5, 6, 7, 8, 9, 10. And then after 10, so from 3 through 10, you need to memorize. Have to know these names. So these 8 terms, okay? Have to memorize these 8 terms. After that, I'm going to let you guys off the hook, and I'll tell you what mathematicians do. This is when we get to the variable n, number of sides. All right? So let's go back to the top. We have 3 sides for the polygon. This is the triangle. When you have a 4-sided polygon, it's what's called a quadrilateral. Now, quad, as in 4, many think of the default 4-sided polygon as a square. A square is a specific instance of quadrilateral. So don't just think square, okay? Next we get to polygon. So agon is the thing that you see at the end of it. The Greeks named these things. So this is there's a Greek prefix, so it's pentagon. So penta would be 5. It's hexagon for 6. Okay. For 7, it is a heptagon. Please name it a heptagon. I get this all the time. Guys, kids are like, oh yeah, Granados, it's a septagon. Okay, that sounds like some sort of like a transformer, right? That's like defending porta potties. No, there's no such thing as septagon. All right. Versus we have the 8-sided figure. We have the octagon. Okay, stop sign. It's an octagon. The is a regular octagon, in fact. And we'll talk about what it means to be regular versus irregular soon enough. 9-sided figure is a nonagon. That's a fun one. And then the 10-sided figure is a decagon. Now, mathematicians, they have more than this. It goes on and on and on. Like, for example, we get to the 11-sided figure. It's called a hendecagon. To 12-sided figure, it's a dodecagon. After this, mathematicians got a little lazy. And everything after n, number of sides, so after 10, we can just literally just call an n-agon. So like, rather than saying an 11-agon, excuse me, an 11-sided figure is a hendecagon, you can just say an 11-agon or a 12-agon. What do you call a 25-sided figure? It's called, I kid you not, it is called a 25-agon. This is what is permissible, because the whole thing with mathematicians, right? We're not exercising linguistics. They are named. I mean, it's fun facts, right? We can go and sit here and name these things. And if you guys want to look it up and memorize them for fun, I'm the guy who does that because this is what's fun to me. But remember, like I'm not very cool, right? I got soft hands. I'm math. I teach math, right? I don't brag about that to seem tough in the world. Yeah, they all have these fun, trivial names. Cool. But after 10, you don't have to memorize it. But 10 or less, you must memorize. Make a big note here for you. Must memorize this table right here, right? And after we get to 11 or more, we just say whatever it is, agon. Okay, let's now talk about the world of concave. versus convex. Okay, this is fun. Now there's another thing we have to define here, and I alluded to this in a previous lesson, which is the notion of what a diagonal is. And what I told you guys is a diagonal is just going to be any line that's going to connect two vertices of a polygon. Okay, it's not a slant. It really isn't. So that's what people think in terms of diagonal. They're thinking of slanted line, and it's because we have this default figure. For example, like to go back to the quadrilateral, right? Our default quadrilateral in the mind is a square, but that's just a single instance, and it's a very specific instance. In fact, when we get to a later chapter, we're going to divorce ourselves from that, or I'm going to encourage you to, and that's maybe not the best way for us to think about the default of a quadrilateral. I'm going to suggest, hey, let's actually think about, let's divide the whole world of quadrilaterals into two parts. It either is a parallelogram or not. And in fact, a square is a type of parallelogram. It's a very, very specific type. But we're gonna, and we'll get there. Trust me. In 4 chapters. But a diagonal is anytime we're gonna connect two vertices. Okay. And they have to be non-adjacent. And that's a term I'm going to get into in the next chapter. Okay. Now, what it means to be a non-adjacent vertex, if it's an adjacent vertex, it's going to make a side. Non-adjacent, for example, in a square, it's that diagonal that's going to be this quote-unquote slanted line across. And again, that has to do with the orientation of the square, and you guys get into that because you want to look at the square a certain way. Well, what if you just kind of turn it a little bit? Well, it's still square, and it exists the same way, and nothing about it, has effectively changed. My big thing on concave, I'm going to give you guys a little bit of the cheat code on this guy. It has to do with the word cave. And these are typically, anytime you guys see the thing cave in. So for example, we had the quadrilateral up above, which was concave and it was a chevron. Okay. So like this guy right here is going to be convex. So this is some sort of a convex polygon. How many sides does it have? It has 4, so this is a right, and look, we're assuming my line segments are, straight. This is a convex polygon, which is a convex quadrilateral, versus this guy. I'm going to draw a pentagon for you guys. Ready? Not going to be how you guys are used to seeing pentagons. Catch your sides there, okay? This kind of looks like a square, but this is not a square. This is the whole thing about like where it's caved in, okay? This guy right here is concave. Looks like somebody kind of took the top of the square and kind of punched the top of it, okay? Nothing's been punched. This is just math, all right? And in fact, I have, let's count them. 1, 2, 3, 4, 5 sides, okay? So this is a wholly different type of polygon altogether. Not even it's classified totally differently. Now, let's actually use this is a great test we have. This is what's called the diagonal test. Okay? Because if I can connect two non-adjacent vertices, let's watch. Well, let's take a non-adjacent vertices. 1, 2. Okay? These guys all happen within the figure interior to it. Now watch this. On the concave, let's take this diagonal. These are non-adjacent, right? Because if I connect right here, that's adjacent. That's going to be just this side, right? All right, let me back that guy out because I'm not going to erase him successfully. But if I connect from here to here, these are non-adjacent vertices. You see what happened there? That is in fact exterior to the figure if I use my diagonal test, which makes it convex. When all of my vertices, like on the convex, right, polygon, that convex quadrilateral, all those guys are interior, that guy is going to be a convex polygon. octagon. Oops, sorry. I think I'm repeating myself. I'm just struggling with my software as I'm simultaneously trying to give you guys this stuff. Okay. Here's a fun one. I want you guys to look at the universe around you. Like I'm looking at a wall in my house right now as I'm broadcasting, and I'm thinking about this in terms of like the doorway. Okay. So here's what this thing looks like. One, two, right? This is a polygon. You guys have polygons all around you as you look. Okay. Take a look at this guy. Now, what type of figure is this? And we start to look at these things and we forget that this is actually not just first of all, is this concave or convex? I think that we have to immediately recognize, aside from like right here, boom, we're gonna do that diagonal test. We go from here to here, and right, and we have our diagonal that's going to be exterior to the figure, making it concave. But how many sides do we have? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. 8-sided figure. This is a concave octagon. I am staring where most people will look at a wall, right? And I've got my doorway right here, right? They'll look at a wall and they'll be like, oh yeah, it's a rectangle, quadrilateral, 4 sides. That's not what I'm looking at right here. I'm actually looking at an octagon because of, what the doorway creates with its concavity, all right, versus its convexity. Next. The perimeter. A perimeter is the length around a figure. Okay? So, let's get down to it right here. I want us to find the perimeter of, and then I'm going to leave a space there. It's this triangle ABC with vertices in the coordinate plane that are A, which is -1, 4. We have B, which is 2, 4. And we have C, which is 2, -1. Saintsman. Few things. Oh, I'm going to teach you guys a little notation right here. Oh, let's not make that blue. Make this black. Mathematicians utilize this little tiny triangle before ABC to denote that this is a triangle that we are creating. So literally, you can prior to writing those 3 points, which are going to be coplanar, makes a triangle. They are non-collinear for it to be a plane. And then it's kind of cool because I've got, put the little triangle up and then it means triangle, not an angle. Step 1 on this, by the way, is that you are not going to graph this. I want to deductively calculate how far each side is. So what I'm going to do is I'm going to take a sum and I'm going to figure out the length of each of these. And look, it's triangle ABC. So I have 3 line segments. I have line segment, right, AB. I have line segment BC, right? And I have line segment AC. Oh man, what's that 0 doing there? What's going on? Okay. Oh, my goodness gracious. Guys, I'm trying to like erase some stuff here and I'm doing too much. Here we go. BC. All right. So AB, how do we figure it out? Well, we're going to use, of course, if I've given 2 coordinates, you guys guessed it, it is the distance formula. This is the way to get the best answer, and the only way I'm actually going to give you credit, as it turns out. So even if you're going to get a integer answer, which we're going to get right now, I'm doing a little spoiler alert, I still need to calculate what that is with the formula. So I have the y's, difference of the y's, 4 minus 4 squared plus 2 minus 1, or 2 plus 1 squared, right? Big square root. 4 minus 4 is 0, plus 2 plus 1 is 3, and that's going to be squared. That and my 0 is technically squared too, but 0 squared is just 0, right? Big square root of 3 squared, right? 0 plus 3 squared, which is 9, and square root of 9 is 3. Cool. BC, big square root sign. Let's do my distance formula. I have, oops, guys, I'm sorry. I'm like you know, the whole notion of fat fingering something. I'm like, my wrist is laying down on the keyboard and creating all those zeros. My apologies. BC, 4 minus 1 squared, okay, plus 2 minus 2 squared. And some of you guys are like, well, hold on. The first time you took the second and then you did the first, it doesn't really matter, right? We've learned that with the distance formula. And if you don't believe me, you can do negative 1 minus 4, which is going to give you a negative 5. And negative 5 squared is, of course, going to be 25, which is what we're going to get if we take 4 plus 1, which is 5, and square it. 2 minus 2 is 0 squared, okay? Which is going to be the square root of 25, which is 5. All right, next, AC, big square root. I'm going to have negative 1 minus 4. Those are my y's. Squared plus 2 minus negative 1, or minus 1, which is plus 1. Negative 1 minus 4 is negative 5 squared is 25. Plus 2 plus 1 is 3. Squared is 9. So the square root of 25 plus 9, which is 34. So rad 34. So what we know is that the figure is the length around, so it's the sum through segment addition of AB plus BC plus AC, which if we substitute, AB is 3, BC is 5, and AC is rad 34. Now we can take here, oops, sorry guys. We can actually do this where we're going to take this sum, 3 and 5 can be combined, which is 8. But rad 34 is just stuck as rad 34. We can't simplify it, so it is just rad 34. All right? Okay. Well, next two are going to be area problems, and these are actually, I think, they should be more difficult, but they're not going to be for us because I'm going to just because watch this. We have triangle ABC with vertices. A is going to be 1 comma 3, B is going to be 3 comma negative 3, and C is negative 2 comma negative 3. So again, this is a triangle. Oops. So this is since it's a triangle, the area formula is 1/2 lowercase b times h, base times height. You've probably heard this before from when you were in 7th grade, because that was a 7th grade standard. You should have been taught that back then. So here we go. Y and x, my two vertices, excuse me, my two, not vertices, my two axes for my coordinate plane. Sorry, I misspoke there. Let's go ahead and just graph these coordinates. We have 1 for x, up 3. For y, we have up to the right 3, and then down 3 for b. So this guy's A, this guy's B, and then c is negative 2, and then down 3. This is letter C. Now here's what we have here. You guys see this thing? There's going to be a counting principle involved, okay? And it's going to be that this line right here, this height, this is your height of 6, yes, okay? Because this guy should have gone right through here. And then counting principle, it's 5 for BC. Now, could you use the distance formula to do that? You should. But this guy exists vertically, and on these problems, I'm going to allow you guys to do it this way. So it's going to be the area is equal to, again, 1/2 of b times h. We already calculated our b, which is 5. Our height here was 6. So 1/2 of 5 times 6, which is 30. Half of 30 is 15. And that's going to be units squared. Okay. And then our last problem here, for our last example, we're going to find the area of ABCD, which you should be able to figure out if it has 4 vertices, then it has 4 sides. Okay, there's the same number. Let me make a note of vertices as sides. Okay, here we go. negative 3, 3. B is 3, comma 3. And C is 3, comma negative 1. And D is negative 3, comma negative 1. I already see that I'm over the mark from where I was previously. So, sorry, I broke my promise, guys, that I was making a shorter video. But this one's good. The area of a rectangle or a square is effectively the same thing. It's the length times the width. Now, the thing is, with a square, or you write L times W, for the square, here's the funny thing, is that the length is equal to the width, okay? Which means it's really the length times the length, or which is the width times the width. So L times L is L squared, or W times W is W squared. We just say it's the side squared, okay? So here we go. Let's go graph this guy in the coordinate plane real quick. Make this guy black. Coordinate plane. This will be a real quick graph. So Y, X. For A is going to be negative 3, 1, 2, 3, up 3, 1, 2, 3. Here we go. That's my A. B is positive 3, 1, 2, 3, up 3 for B to graph it. C is positive 3 and down 1 for C. And then it is for D is left 3 for negative 3, down 1, right? And this, we have created a rectangle. So this is the area. It's equal to L times W. This length across here, my W is equal to 6. My length here is equal to, counting principle, 4. Very straightforward. 6 times 4. So my area is equal to 24 units squared. All right, gentlemen, I hope you guys are ready. Those area problems are going to be very straightforward in terms of you're able to use counting principle. However, perimeter, you must use the distance formula. So beware. Be ready for that when it comes time for your assessment. Good luck.